Sir, could you please upload the lecture notes of the previous two lectures too?
Yes, Rishan. Yes, Rishan. I after this today's lecture, I will do it immediately.
Thank you, sir.
Okay. So yeah, this is the second part of today's lecture. So we have started recording it again. So okay. By the way, so I have already uploaded the practice paper 3, which is where you can see the questions from the DC biasing part of bipolar junction transistor. So which we have almost covered. So I request all of you to please try those problems, try to solve those problems, okay, by yourself first. So maybe in 1 or 2 days, maybe in three, maybe yeah, by this weekend, I will also upload the solutions of this practice paper 3. But before that, I request all of you to please try out those problems by yourself first. Okay, so then we have seen like how BJT can be used as a switch, how BJT can be used as an like as an digital like for making different digital logics, right? So okay, I think before we go to this part, I think I forgot to mention one thing here. So what is this gate? This gate we have understood this is basically NOT gate or inverter gate. So what is this gate?
Not
NOR, are you sure? It is NOR gate, right? Because here you can see
XOR.
XOR. No. So when both outputs, like both the inputs are 0, then only the output is 1. When at least one of them are 1, right? One of the input is 1, the output is 0, which is basically the opposite of this OR function, right? It's not, isn't it? So this is basically NOR logic. So like that, you can make, you can also try to make, please try to make this NAND gate. Please try to make this AND gate. Okay. And please try to make this OR gate. Okay. Using this transistor. This is you as a part of your homework.
So,
Hmm.
I had a question. Why would we create these logic gates using BJTs instead of simple diodes?
Using diodes, you can get some of the logic function, but not all the logic functions you would be able to implement. Okay, maybe huh? Maybe maybe in the some of the tutorial class, maybe in the BJT tutorial class, we can take some examples on that. Okay. So yeah, so let us come back to our discussion. This BJT as an amplifier, right? So here you can see a simple circuit, very simple circuit, right? Where this is VCC connected with this NPN transistor. Here, this is one resistance RB through which the input voltage VI is been connected, right? But we are using amplifier, right? Amplifier means it is not an amplifying some DC signal, right? We should have some AC signal which this transistor will amplify. Maybe suppose like our voice. Okay, when we talk in front of this microphone, our voice will, this acoustic signal will now get transformed into the electrical signal. And maybe that amplitude of the electrical signal would be very small, and we need to amplify that signal. Amplify the signal means the signal property, this frequency and all stuff would not change, or it will replicate the same signal, but it will make the amplitude higher. Or, that the only the amplitude will increase, right, in the output. So that is basically an amplifier. That is basically what an amplifier does, right? So obviously at this input we need one AC signal, right? So say this is that AC signal VI, say, or this V source, say V source. We have already given VI, so let us use V source, right? So this is the AC signal. But the thing is that if we suppose and make here ground, then will this work? The thing is that this will not work, right? Because this signal, this source signal will be so small that it would not be able to make this PN junction forward bias, right? So we have to apply additional DC voltage to make sure that this junction is forward bias, and that is what the biasing means. You remember, I think in the first class itself, we have discussed like in the content, like what is the importance of biasing. There you have some difficulty. I think now from this point onwards, it would be much more clearer to you. Okay, so we cannot only apply like here only an AC signal source and say like this this transistor will behave as an amplifier. We have to make sure that the transistor is biased in the forward active mode. So for that we have to apply one battery here, VBB, right? And when you suppose remove this VS, if you remove this VS, if this VS was not there, only VBB was there, then obviously this is the V output versus V input characteristics would look like this, right? So now do not consider VS, only this is VI, and say this VI you can change, or right, VI you can change means VBB you can change. So that means you can change VI. So now we have seen this V output versus V input characteristics in today's class only, right, where we have seen the output characteristics would look like something this. So this is around 0.7 volt, this is around 1.9 volt for the particular case which we have done in today's one of the example. But those values are also dependent on the circuit, other parameters of the circuits as well. So you have to find these values, like this values is 0.7 is fixed, but this value depends on the other circuit parameter. So you have to find this value, right, from the equation that we have derived today. Right, but and we have also mentioned when this transistor has to be operated in the as an amplifier, then the transistor has to be biased in the forward active mode, right? So here also the concept of this Q point will come. This here, say like we have biased the transistors somewhere here, okay, somewhere here. So this is basically the Q point. So that means we have given the input voltage of this much. So what is this input voltage? This input voltage is set by this VBB, this DC supply voltage only. Okay, so we have chosen DC supply voltage such that the VI is this much. As a result, the output is this much. Fine. Okay. Now on top of it, now we have additional signal source which is VS, right? And VS is a sinusoidal signal source. So VS is changing, right, with time. Okay. So let us now say this VS is changing. How can we demonstrate it? So say this VS is changing, right? VS is changing like this, the sinusoidal. And here, say this is the time 0. Okay, this is time 0, and you have this increasing time in this direction. Okay. Now, if this is the amplitude of the signal, right, of this like peak to peak signal of this VS, right, then when you are changing, means when this VI, see now what is VI? VI is basically VBB plus VS, right? So as this VS will now change, VI will also change, right? So when this VI will change, this Q point will also change, right? So when this VI is this, Q point was this. When this VI is here, right? When this VI will go and reach this point, then this Q point or this transistor will be operating in this region. Now when it will come back to this, the transistor will again come back to this region, right? When this when this VI will now become this, right, the voltage the Q point will also change here, right? Now what actually basically you can see from here. So see from here, when this VI, remember that VI is equal to VBB plus the sinusoidal signal VS, right? So when this VI is this much equal to VBB, though we know this output, this Q point is this. So if you take a projection from here, we are doing it graphically first here, and say here also the time equal to 0, this point, right? So go to this pointer, take a point across here. Right now, as the time in progress, right, the signal is increasing. The signal increases and the signal reaches here. Now, when it comes to here, right, this take a projection along this line, take a projection along this line, and time is increasing in this direction. Say here, then this point will go down, 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 and reach a point here, somewhere here, right? Reach a point somewhere here. So let me save it once. Yeah. Right, then again the signal comes down, go reach here, then take a projection along here, take it here. So signal will again go down, reach somewhere here, right? Then its signal will come here, then you will get a projection along like this. Right. So you can see if this input signal is changing like this, all right, see the change in the output signal. The change in the output signal is like this, right? Right. So, and obviously we have also discussed this in our previous discussion that if you want to use as an amplifier, then in that voltage transfer characteristics, the slope has to be greater than 1, right? Then only the output voltage, the output would be amplified compared to the input. So you can see this input sinusoidal signal whose amplitude was earlier this much, right? Now this amplitude has been magnified or amplified to this. Right. So this is basically the amplification. So you can see this is the same sinusoidal signal, even though it looks like it's this time has changed, but then it is not the correct way to judge this because it is a hand-drawn diagram. So you can consider the time axis are different. Okay, maybe say okay, maybe let me write it here. Say this is 0 to t by 2, and this is t. Then here also it is 0. This is t by 2, and this time period is t. So this time period is exactly the same. Only thing that is changing is the amplitude. So you are getting the amplified version of the input signal. Right.
Sir,
Yes.
sir, here the signal is also phase shifted by pi.
Yes.
Should
Yes. Very good. Very good. Yes, you are right. You are right. So here, as your friend mentioned that if you see this signal, input signal is like this. So it is starting from 0, right? At 0 is 0. Then at t by means at t by 2, it is like means at like t by 4, it is reaching the maximum. But here you can see at t by 4, it is reaching the minimum. So you can see there is an phase shift, right? Now the thing is that is this phase shift is this expected this way? And if you analyze it a bit carefully, then you will also see that it is expected because you see this when Vi is increasing. See this. Please follow my this point of cursors. Okay, if this Vs is increasing or this say this Vi is increasing overall. Say if this Vi increases, what will happen to Ib? Ib does also increase, right? Do you agree with me? Yeah, please, you have to tell me if you do not agree.
yes, sir.
Okay, because see, what is this IB? IB is nothing but VI minus this V of BE on, right, by RB, right? So obviously, if these things are constant, if this VI increases, then obviously IB have to increase. So if this IB increases, right, then what will happen to IC? IC will also increase, right? IC will also increase. Now, what is this V output? V output equal to VCC minus IC RC, right? So, if C this IC increases, then what will happen to this V output? V output should reduce, right? So, it is expected from the circuit analysis as well that there should be an 180-degree phase shift between the input and output signal. So if the output signal you have taken from here, then you can see an 180-degree phase shift in the output signal, even though it is amplified.
Sir, shouldn't there be any effects? Because we are giving an input and we are getting an output which is phase shifted. So,
No, it is not an big deal. So we will discuss that. In CE amplifier, in all cases, we will get an phase shifted output only. Phase shift, you can use some other techniques to get the make it correct, right? But the important thing is that whether you are getting the amplification or not, that you are getting that amplification. Okay. So here I think you have noticed one very important thing is that the importance of here this VBB, right? Because VBB only makes sure that the midpoint, okay, the midpoint, this point is should be in this forward active mode only, right? Because this VBB only establishes this midpoint, right? That's what we have mentioned here. So if you have chosen VBB carefully, then you if you have to make design one amplifier, then you have to design this Q point almost in the midpoint of this forward active mode region, so that way you have sufficient space in the below, sufficient space in the above. So that means you can fruitfully amplify and sinusoidal signal. Now, say for example, in one case, you by mistake, you have made a choice such that this Q point is staying somewhere here. Okay, Q point is here, right? Then see what would be the trouble that you have to face. Now again, see the input signal. So this is the midpoint, and this is due to say this is due to VBB only, right? And then you are changing the input signal, and say the input signal is this way, right? This way. Now, if you go try to draw its the output graphically, right? Then when it is this input, it will go and reach here. So take a reflection, make it here, right? Then when it reaches here, see this reflection is here, and you're going to go come back, right? So this comes almost here only, right? So you are not getting anything here, right? It is here only, right? Again, you come back to this point, so maybe somewhere here. Then you can go below. When you go below, then it you can see it can get amplified up to here. When it's coming back here, so you are getting somewhere here. So more probably you will be getting a output curve, output characteristics, which is somewhat like this. Output, this is input, right? So you have seen that here everything is the same, right? In the circuit we have only changed the value of VBB such that the instead of putting the Q point here, you have put the Q point here. So now you can see the this the positive half of the signal is completely getting type of clipped here, right? Or it's not able to amplify it. So you are not getting nothing here in this, but you are getting only the amplification of this negative part. So that way, I think it gives you an impression, like you can understand that then how important it is to keep this Q point okay near the middle of this point, right? Near the middle of this active region, right? If you do not do that, then this type of things will happen in your final output, right? So it is very important that you should bias your transistor properly. Otherwise, you have to face this type of consequences, right? So in the same token, you can also think that if there was no VBB, right, then this Q point would be somewhere near to this here, right? And then you have only this positive half and negative half. Then for this positive half up to this 0.7 volt, you are not getting anything. Then after that only you will get some output. So that is the reason why without biasing your amplifier or none of this, not even any, any amplifier will not work until and unless you bias the transistor properly. And that is what we have discussed during the if you can recall in our first class, okay, that if you cannot do biasing properly, then that amplifier will not work, even though you have this signal source. So this signal source alone cannot bias the whole amplifier circuit, right? So you should have here VBB, that is important. At the same time, it is also important along with this VBB, you should also have this VCC. So suppose in your laboratory also, if you forget to connect VCC or in maybe the supply voltages, then ultimately you will find, even though you have connected all this input signal and everything is correct, you will at this output you will not get anything, because the transistor will not behave as an amplifier until and unless you make the proper biasing. Biasing means the DC biasing. Okay, so here one small term before we move to the next one, the next part. So that is called this, which color I can pick? Yeah, that is called this amplification factor. So amplification factor is nothing but actually the slope. Actually, this V output or the primarily it is written as delta V output by delta V input. Okay, in this forward active mode. In forward active mode. So if you know these values, this value, this value, this value, this value, this value, then you should be able to find what is this amplification factor for a particular transistor. Okay, so this gives an impression obviously to all of you that so how important it is the properly this importance of this biasing a transistor, right? Now, in the next part, we will discuss about this biasing only in more detail, that how to bias. Okay, so but before I go to this section, here you can see in this circuit, what we have done, we have used two different sources, right? Two different DC voltage sources. One is VCC and the other one is VBB. So two different sources, right? First thing is that we will try to reduce the number of sources as low, try to minimize it, right? So we will try to see if instead of using two, if we can use only one source. That is our first goal. Next thing is that here this VS or the signal source is being connected with in series with the DC source. Generally, we always try to avoid that because we avoid the DC current to be flowing through this signal source, right? So we do not want to connect the the signal source in series with the DC source. So that is another one. And in another way of thinking why this is not a good design, that is because here, see, for generally any signal source, okay, suppose if it is for antenna, then it will be one part would be the signal and the other part would be grounded. Okay, but here you can see the here like you don't have any ground terminal for this GS. So considering these 2 points, we'll try to improve our like this circuit, particularly this circuit in the next page. So here we have drawn it like this so that we can make similarity or we can make our discussion similar to the previous discussion. But now we should also understand what is the drawback of this. You cannot really make a design like this. So here in biasing, so we can use probably, there are primarily like two techniques that we were going to discuss regarding the biasing of BJT circuit. One is the biasing using a single resistor. So in here you can see you have this VCC, we have this RC, we have this RB. So RC you are familiar with, right? You now just forget about this part. Just a minute. You for the time being you forget about this part. Just consider here this other part, right hand side. So here you can see this is RB connected with the base directly. So what we are doing here, we have to forward bias this junction, and we are doing it forward bias by connecting this VCC, a positive voltage, through a resistance RC with this. Fine. Okay. So that way we have made this VBE like positive or 0.7 volt. So we have made this bias point. Fine. Okay. Now there is a question of like the how to input the signal, and the signal has to be given input at this base terminal only. That is what we have discussed when we are discussing here the BJT as an amplifier. So you can see the input signal is applied in this base terminal only. So you have to apply the signal to this base terminal. So how can you do that? So this is the signal. Now we take the signal, but we will not directly apply the signal here, but we will use one capacitor between this node and this node, and through this capacitor only we will connect VI. Now the question is why we need this capacitor. We need this capacitor because there was one question earlier that we discussed that we do not want any DC current to be flowing through this signal source, right? And to block the DC current, the capacitance is a good choice because this capacitance will behave as an open circuit in DC, right? So if you have this capacitor here, then the current which is flowing through this RB from this VCC will not flow into this VI. That is one thing. Now the other thing is that as this is the AC signal, so it has some particular frequency, and we will choose the value of CC or this capacitance. This is called the coupling capacitance. Okay, coupling capacitance. We'll choose the value of this coupling capacitance such that for this frequency and for this value of CC, the like impedance offered by this capacitance would be so low that we can neglect it. So that means we can consider that this CC will act as a short circuit. Means for this signal VI, the CC is simply a short. Okay, but for DC, it is an open circuit. Okay, so you have to remember here two things. One is the frequency of this input signal, and the other one is value of coupling capacitor. Okay, these two you have to consider, because the impedance, this XC, this is 1 by omega C. I am not writing this j omega C, so 1 by omega C, right? So more you have omega, the less would be, the more you have omega, the less would be this impedance of it. The more value of this capacitance, again, the less would be this XC. And you want that the value of XC to be as small as possible so that you can consider it as a short circuit, right? And typical values of CC will be in microfarad range. Typical value, right? So, and this microfarad capacitance are actually, they are very high capacitance. Actually, this microfarad capacitance, these ranges are very high. So, you understand how this, how you can make this amplifier circuit, or how you can design this amplifier circuit. But here, instead, you see, we do not need that VBB anymore, right? VBB we have replaced it, right, by using this RB only. Okay. Now we are in analyzing the biasing part, right? Biasing part means only the DC part. So we should focus only the DC part. So when you consider the DC analysis, when you do the DC analysis, this capacitance can be considered as an open circuit. So you neglect this total part because it is not there. So the circuit basically becomes like this, like as simple as it is, right? Very simple circuit. Now we have to consider here, like what would be the current, voltage, and all these relations for here. That is very simple. We have to find IB. So basically this IBQ, because it is the, it will be the quiescent value of this, right? So what will be the value of IBQ? It will be VCC minus V of BE on, which is basically this part. This is VBE on by this RB, right? Then what would be this ICQ? ICQ would be equal to beta IBQ. So which will be equal to beta value, beta into RB, right? So you can see from here that this IC, see this ICQ is now proportional to this beta. So that means, if suppose you have designed a particular amplifier using a transistor whose value, which with a particular value of beta, then if you replace this transistor with another transistor, then obviously its beta value, I told you, no two transistor has similar beta, its beta value will change. So if you replace this transistor with another transistor, that will change your ICQ as well. Means your collector quiescent current will also change, right? So that way we can say this biasing technique is not very stable in terms of the variation in beta. To understand it clearly, consider that we are consider a case, consider this IB equal to say 10 microamps. Okay, so IB equal to 10 microamps, right? Now you are changing the, suppose you have designed this transistor. Now suppose this at first the current through this ICQ was so high that the transistor got burnt out, and you have to replace this transistor with a new transistor. So earlier say the transistor beta was this beta 1 first, and you have a Q point here, right? Q point is basically this is the, this is the value of ICQ, right? So ICQ1 actually. How can you find the value of ICQ1? It will be the value of IB. IB is same because you are not changing this RB. It is same. So IB is same, but the value of beta U is changing because you are changing the transistor. Now suppose you have changed the transistor and the transistor beta value is beta 2. So your Q point has now shifted from here to here, right? So remember, we are not changing IB. IB is fixed because it is of this circuit, right? But we are changing the transistor. So, and if due to the change in transistor beta value changes, then you can see the Q point also changes, right? And what it makes, that means in one case for one transistor, you are getting ICQ like this, and here you are getting ICQ, which is something different, right? Similarly, you can see that will also make a good amount of change of this, that like this is with delta of V of CE. So delta of V of CE and means V of CE will also do a change, and IC will also make a change. right? So that way you can say this circuit or this particular biasing scheme is not very stable due to the change in beta. Because it might happen, right, that you have designed it for suppose for a transistor with beta equal to 300. Then, but in practical life, when you are making this, you got a transistor whose beta is say 200. Then you have to, otherwise you have to design the entire circuit once again. You have to change the resistance, RC value once again. But we want to make a circuit, so we want to make the circuit such that this type of change will not impact the circuit performance much. Definitely it will impact to some extent, but we should try to reduce that. So I hope then this point is clear to you that why why it is not very good not very good way to bias a particular transistor.
Sir, if we are
Sir,
neglecting capacitor during all calculations, then why do we need it at all?
No, we are not neglecting in all calculations. Right now we are focusing on the only on the biasing part. Biasing means the DC biasing part. So DC biasing part, we should consider only the DC part. Here, why we are showing it? The question is, why we are showing it? We are showing it to give you an idea how the actual circuit would look like. Okay, and we are not neglecting. I mean, we cannot neglect it. We cannot neglect the AC part. That part we have to consider. We have to consider it maybe bit later on. But right now we are focusing on the DC part. So we are only focusing on the DC circuit part. But yes, we have to take this part as
Sir,
well.
will that AC source affect the value of IB?
This AC source will definitely affect the value of IB, because this will change the value of this input voltage. But there are two terms actually. If you consider here, there are two terms. Suppose this, if you consider this input voltage as VI, then VI has two terms. Only due to the DC part, and the other one is due to this AC part. Right now we are focusing only on the DC part. So right now we are not considering the change in IB or this input voltage due to the change in this input signal. Is that clear?
Okay, sir.
sir,
Okay.
then like in DC part, we are just taking VBB equal to VCC for normal transistor, right?
VBB equal to VCC for normal transistor. Uh,
It is
yes,
something like
that way you can say it like that. But yeah. If please first complete your point, then.
no, that is means we are just taking VBB equal to VCC for normal transistor and we are neglecting the capacitor. Means capacitor part, yes.
Right, but this will come at some cost. See, what is the cost now? Say this IB, right? This, what is the typical value of IB? Typical value of IB will be in terms of say like some microamps. Okay, typical value of IB. Okay, in microamps, say like 10 microamps, typical value. So if this IB is 10 microamps, then from here we know this is V of BE on, and say this VCC is say 12 volt. Then can you find what is the value of RB? What will be the value of required RB? So how can you find required RB? It is VCC minus VB on, right? Simple, right? KVL. VB on divided by RB.
Sir, IB.
IB, right? So can you please give me the value?
113 into 10 power 4
Yes. Unit?
ohms.
Are you sure?
Yes, 113 into 10 power 4 ohms. Yes.
Oh, 113 into 10 to the power 4 ohms,
Ohm.
right? So then if we take it, if we can also write it like 1 point this into 10 to the power 6, which will make it mega ohm, right?
Yes, sir.
See here, this is the cost. if you connect it like this, then the value of RB have to be extensively high, which will be in the mega ohm range. Very high value, difficult to implement in integrated circuits. In integrated circuit, it would be always, remember that it is always difficult to implement a very high value of resistance. It's difficult, not technologically difficult, but it will take a huge amount of space. Okay. And in IC, the space means the area. Area is everything, right? That's how you are getting, billions of transistors, in a small chip. But if you, for one transistor, if you need this much mega ohm, that means you need a huge amount of area to implement this resistance on silicon. So this technique is not preferred. From this, first thing is that the biasing Q point is not very stable in terms of change in beta value. And the next point is the required value of beta will also become so high that would be difficult to implement.
Sir, isn't the previous model sensitive to beta?
Huh?
The previous model, like
model.
where the DC source is in series with LC. Yes, sir. Here.
DC source is series with this one here, right?
Yes, sir.
Yeah, but we have also discussed now difficulties here.
Yes,
That one
sir.
is this DC current is flowing through this.
Yes, sir. But here also it is sensitive to beta, right?
Here also it will be sensitive to beta. Yeah, here also it will be sensitive to beta. You are right. Yeah,
Then,
you are right. So
sorry,
we are, yeah. So we are trying to, solve that. We have still not solved it. Okay. So this is one technique, but we have seen this technique is not very useful. But here, one thing is that we can get rid of two voltage sources. Now we can use only one voltage source, VCC, and use it. And the other thing is that other difficulty that this voltage source, DC voltage source and AC voltage source, which was earlier in series, we are also, that issue we can also overcome in this design. Yes.
Sir, for the capacitance part, you told that we are changing the value of omega and capacitance value such that it behaves as short circuit.
Not changing. We are choosing. We are choosing.
Yes.
Right.
And and then you are saying that for DC analysis it behaves as open circuit. So how
Yes.
can it behave as open circuit and short circuit at the same time?
No. Okay. Maybe this part you have misunderstood. Okay. What I have tried to say is that, see, this signal, right? VI. Okay. Hello.
Yes, sir, you are audible.
Yes.
Yes.
So suppose if this frequency is low. Okay. If this frequency is low, what would be the impedance offered by this capacitance?
High.
High. So if the impedance offered by this capacitance is high, then what would be the drop across this capacitance? That would be also high.
Yes.
Okay. Then what would be this voltage? If you just say, means see this VI, if you again apply one KVL, small KVL here, then this voltage or the voltage at this node, okay, voltage at this node would be equal to this voltage, AC voltage, minus drop across the capacitor. Do you agree?
Yes, sir.
Okay. Now, if the voltage drop across this capacitor is more, then more part of VI will be dropped across this CC and less part will be coming across in this node.
Yes, sir.
Okay. So that's what I'm saying, that for our design, we have to make sure that that we are choosing this omega and the capacitance value such that for AC analysis, this capacitor will behave as a short circuit for AC analysis.
Okay, sir, understood.
Okay, but
Yes.
that we are going to discuss a bit later on. Okay, but right now we are focusing only on the biasing part, which is the DC biasing part. But this part is only I have discussed in the context of AC analysis. For DC part, we have to focus only on the DC, and for DC, this capacitance will behave as an open circuit. So we should neglect this part, this the part which has been enclosed within this red line.
Okay, sir, understood. Thank you.
Welcome. The other way would be to use a voltage divider biasing with emitter resistor. So here we have used this VCC, right? This is RC. This is we are familiar with and is connected with the transistor. And here in the similar to the previous example, we have seen like we are using this resistance R1, which is connected with the base. But at the same time, we have also connected R2, which is connected with this ground, right? And in addition to that, we have also added one emitter resistor. So you can see this emitter resistor, okay, which is connected at the emitter terminal of the transistor, right? And similar to the previous case, then where to fed the signal has to be fed at this base, and the technique would be like this Vs, and this is this coupling capacitor, and through this it will fed. Again, the similar analysis like before. This is the DC analysis part. This is just to show how to fed the input signal, but for DC biasing part, this has no, this has no concern. We should not concern this part for DC analysis. This is just to demonstrate you how to fed the signal. So for DC analysis, the resultant circuit is like this, right? Now to how to handle or how to analyze this type of circuit. The process is we have to find what is the use Thevenin. Okay, use Thevenin and find what is the equivalent resistance if you look from this side, and what is the equivalent voltage source if you look from this side. That means the Thevenin equivalent circuit of this part, this part, this side part, left side part of this green line. Okay, so then what can we write? Then we can write Thevenin equivalent voltage VTH. VTH would be the drop across this, right? So, and that drop would be equal to this VCC into R2 by R1 plus R2, right? What would be the equivalent resistance? For that, you have to remove VCC, right? Then this part is grounded, this part is grounded, and you are looking from here. So R1 and R2 are in parallel. So RTH would be equal to R1 parallel R2. Then if you think for the equivalent circuit part, then this equivalent circuit is like this, right? This is this equivalent part, right? Right? We have replaced this one with this VTH, Thevenin voltage, equivalent voltage source, and equivalent resistance, right? And this is like similar to VCC, RC, RE as it was earlier. This right side of this. This is the right side of this. Now, this circuit, now it would be much more easier for us to analyze this particular circuit, right? And if you now use this circuit and analyze it, then we can write this VTH, right? We can write VTH is equal to IB into RTH plus this VBE on, right? Plus this IE RE, right? Because this is IE, right? This is IC. Remember that. And this is I. And let us say this is IB only. Let us not write IBQ. So IE only. Okay. Then we also know that this IE, we can write it as 1 plus beta of this IB, isn't it? IE equal to 1 plus beta of IB. So if you now substitute that here, it would become VBE on plus 1 plus beta IB RE. So you can see you have IB terms here. So you can take a common and you can try to find the value of IB from here. So if we now do it, it will become IB will be equal to VTH minus VBE on divided by RTH plus 1 plus beta into RE, isn't it? Just solve for IB from here, right? So now you have the value of IB. Then what would be the value of IC? IC would be equal to beta of IB. So just write the value here. This beta into this VTH minus just VB on by RTH plus 1 plus beta into RE, right? And we need some more space here. Yeah, so now you see this is the value of IC, right? Though this is important, this is the value of IC, right? Now if suppose we choose the value RTH such that RTH is much less than 1 plus beta of RE, that means this part is much less than this part, then we can neglect this part, then IC will be nearly equal to VT IC will be equal to this beta times of VTH minus V of BE on divided by 1 plus beta into RE, right? Again, what is beta? Beta is much greater than 1 because it is 100, say like in the range of 100. So that way we can write 1 plus beta is also equal to beta, right? If you do that, then you can see this part and this part you can like cancel out actually. So IC would be equal to VTH minus VB on by RE, right? So if you now notice this last expression that we have derived, then you see this IC is independent of the value of beta. Independent of beta, right? So that means previously we have seen that if the beta value changes, that will affect the value of Q quiescent, but that will also change the quiescent point. But if we use this technique, then we can see this IC is independent of beta, and for to make this IC independent of beta, we should have chosen this condition. If this condition valid, then we will get this criteria. Now the question is, then why means what is so special in this circuit for which we are getting IC independent, or the biasing point is becoming almost independent of beta, or the beta or this Q point is become so much stable? The reason behind is not here these two things. The reason behind is not this R1 and R2, but rather it is this RE. RE is the important part which is actually stabilizing the quiescent point. Now the question is how RE is stabilizing. Okay, then please try to think in this way. Suppose if this beta value changes, okay, if beta value changes, then IC will okay, if beta value change, then will it change the value of IB? No, IB value will not change. The only value that will change is the IC, obviously IC and IE. So if IC value changes, then IE value will also change, then IE value changes. And see, if this IE value changes, that will create a drop, additional drop across this RE, right? So if this IE value increases, that will increase a drop across this RE, right? Okay. Now you see from here, consider this loop, consider a KVL along this loop. Here, this voltage would be equal to VBE on plus this, right? Among which the drop across this is fixed. V of BE is expected to be around 0.7, but now you are increasing a drop across this RE. So what does it mean? You cannot change the drop across this R2 because that is flowing through from VCC. So, but you are increasing a drop across this RE. So, from this KVL, it should be clear then if this drop across RE has to increase, then somewhere some voltage has to be dropped. So that voltage drop will occur across this. So the voltage drop across V of BE will now decrease. So you know that voltage drop when V of BE will decrease, then what will happen? It will reduce IC, right? Basically, in the other way, it will try to give a negative feedback effect, okay, in this circuit, and in this way, it will try to stabilize the bias point or the Q point. Is it clear? Is this point clear to you?
Sir, could you please explain again?
I think it's already, 10, more than 10, just 1 minute past. You have a class definitely. So maybe it would be a good if you can, we can explain it in the next class, right? Otherwise, it will be late for you to join the next class. So, okay. So this negative feedback part we will explain again in the next class. Okay. But I request all of you to please go through the part that we have discussed so far today. Okay. Okay then. Thank you.
Thank you,
Thank
sir.
you, sir.
Sir, you will be releasing these slides before the